Now, what we're going to try to do is make a primitive magnetron. Now, these things, all of these are designs that were made back in the 30s, maybe as late as the 40s, but these were mostly in the mid to late 30s. In these magnetrons here, the axis of the plates is placed perpendicular to that of the tube. And that's made to where the tube will fit in a pole piece like so. You take like a horseshoe magnet and the magnetic field is parallel to the axis of the plates. Now the other type of magnetron, the plates are placed parallel to the axis of the tube, and then you put the magnet, which would be a like so, with the pole pieces like that, and the magnet would be surrounding the tube, and it could be even a coil of wire. Back in a long time ago, when they were doing this in the 30s, they didn't have magnetic materials. Alnico was unbelievably expensive back in the 30s. It was one of the most expensive materials there was, because they didn't have the capability of producing large quantities of it like they do, like they did, in the 50s and 60s. It got to where they were producing tons of this stuff, but that was much later. I'm going to go ahead and make, since I have several of these big magnets here, I'm going to go ahead and make a one that goes across, perpendicular. So this particular way of making it is not very smart. This is back to the old double-ended method, similar to what DeForest did with his spherical audion. He had stuff sealed into one end and then had to go in from the other end and somehow align this thing up while doing the glass work. Now that is just outright stupid. It's not smart. So what we're going to do is we're going to arrange to have the entire electrode assembly supported on one end, and then we slip the envelope over it and do the glass work. That way we can align the cathode and the cylinders perfectly before we do the glass work, and wind up with a lot more concentric assembly without the nightmare of trying to get not only the angular position correct, but the centering correct and the longitudinal centering correct. That would be a nightmare. I can't imagine how they could be so stupid. But hey, back then they were desperate. They did not think. All they did was act. Okay? Even Phillips, okay, this one here is a Phillips design that I found on the internet. It's the same stupid double-ended type of situation. They had to sit there and do glass work while they were trying to align the cylinder to the cathode assembly. That is how can they be so completely thoughtless? Okay. All right, so what we're going to do, okay, we'll make a seal, and we'll have the wires coming through the seal. This will be glass here, and that'll come back around, and the cylinder will seal onto that. That'll be the cylinder, and it'll seal here. So what we'll do is we'll take this seal here, and we're going to have two coming in, and we're going to fasten our cylinders onto that. Okay? This is side view of the cylinders. We'll have one here and then the other one facing the other way down on the other side. Then what we'll do is we'll seal two more wires, which will come up here like so. And we'll do on the other side. See, we'll just seal those wires into glass. Now, we'll take on one side, the cathode will be in the center of this. and that'll come out and it'll weld onto here, and then the other end of it will weld to the other one. Okay, that'll give us our two connections for the filament. Now these will be isolated from the RF output. If we look at this from the side, the seal will look like so, and we'll have our two coming up here. Okay, and then that'll be our side view of our plates. Okay, and those will go on through. See, and this will come around like that. See, and this is solid glass here. Okay. See, and then the cylinder will come up like so. And what we'll do then is the other wire will come up here like so. And that'll be sealed into glass. So we'll have no contact between here and here. That'll be isolated by the glass. And then our filament will be right in the center of there, welded onto here. Okay? So that'll make it to where we have got the axial alignment, the longitudinal alignment, and the angular alignment, all of it referred to this one seal on the end. Now, when we do the other end of the tube, what we'll do is we'll have a pinch seal. This will be the tube that's coming back down to seal it. And what we'll do is we'll make the pinch seal have two tunnels in it. Okay, we do that by using some carbon. And we take these wires here, and when we put that together, we'll take them and we'll arrange them to go up into that pinch. Like that. And then we'll have our tungsten seal, and then our electrodes coming out the end for the filament. Okay, and then once we get that in there and we get this end sealed, we'll then reheat this pinch and pinch it to make the seal, and that will seal off the tube. And then, of course, on one end or the other, we'll put an evacuation stem to pull a vacuum on it. Okay, that way we eliminate the problem of trying to work double-ended on this thing, because the only thing we'll be doing is shoving it down, and we just have to make sure that our two tungsten seals end up in the pinch, and that'll be very easy to do compared to trying to align all this other stuff. All right, so the first thing we're going to do is we're going to make up this pinch right here. Now we're going to make the whole thing to fit one of the magnets. Let me get one of the magnets. All right, this is the magnet. It's a strong sucker. I mean, that thing is strong. Now, there are two things about the magnetron. The strength of the magnetic field determines how much voltage it takes to go ahead and reach cutoff. Okay, if we draw the magnetron, okay, if that's the plate assembly right there, and the cathode's in the middle, we're looking straight down on it. Okay, if we have no magnetic field at all, when the cathode emits, the electrons will travel straight out to hit the plate. Now when we put a magnetic field, longitudinal on here, in other words, the north on the top and the south on the bottom, then it's insurance salesman. I'm not even going to answer it. The electrons will tend to be diverted. They'll curve, like so. And if we make the field strength strong enough, the electrons will just completely curve in a circle, like so. And at a critical point of voltage and magnetic field, the electrons will go in a circle around the inside of the plate. And when that happens, a negative resistance occurs, and the tube will start to oscillate. The voltage will increase slightly, causing the field to move in, and it'll decrease slightly, causing it to move out, at which point the electrons will hit the plate, giving plate current, and that will increase the axial magnetic field slightly, and that causes the electrons to move back in and break connection, and they go in a circle again. And this goes back and forth like that at a microwave frequency, at just absolutely unbelievably fast. It can be up in the gigahertz range. And the strength of the magnetic field determines how much voltage that it takes to get these electrons to curve. Now, on the other hand, the output power is determined by the current and the voltage. So if you have too low of a voltage, then you get very little current, so the total output power is low. So while it may be easier and take less magnet to go ahead and cause it to oscillate, the amount of output power will be much lower. It could be 10% or even 1% of what it is if you start really running the voltage up. Typical magnetrons will run anywhere from several thousand volts, like 2,000 volts or so for a magnetron in a microwave oven, to 20,000 or even 30,000 volts for a magnetron that you find in a like a radar set for a ship or something, ship radar or airplane radar. So for this magnet here, I'm guessing just from looking at other various magnetrons, it's probably going to be several thousand volts. It'll be up there in the 3,000 to 4,000, maybe 5,000 volts that will it'll take to go ahead and overcome the magnetic field off of this magnet. So that's no problem. We have power supplies that'll do that. Okay, so that looks like our diameter can be anywhere up to about 1.25 inches and fit in this magnet. Okay? That'll make it a little bit easier to make these plates and things. All right, let's find some glass tubing and get started. Okay, first we're going to make a beginning pinch. We're not going to do the full pinch. We're just going to get it down flat so that we're ready. And then we have to make up the electrodes and pinch them in there. That to work this side of the tubing, we have no problem with one oxygen concentrator. We're using one oxygen concentrator running at full power, 5 liters per minute. And we can work this 1-inch diameter boro without any problem at all. Okay? Okay. The next thing we're going to do is we're going to put our electrodes in there and pinch it down and seal it. Okay, first thing we do is we take our tungsten and we slightly oxidize it. cool down slowly. If we were doing this in soft glass, we'd have to cool this over a period of an hour. We should be able to get away with this, you know, doing just a few minutes. Okay, now we keep it cooling. By keeping it rotating, it keeps it cooling evenly on all sides. If you stop it before it's cool, I mean the top half will cool slower than the bottom half. The heat rises, so heat from the bottom will keep the top hot, and you'll have uneven cooling. But by keeping it rotating until it gets down below about 500 degrees, then it'll cool evenly. Alright, everything's cool. Cut this off now, and then we'll get busy at the rest of it. Okay, I want to definitely put something down to catch. Don't want it to fall and break. There. See if I can catch it. He wanted to crash. Seals look perfect, and everything's all stuck in there. Now the envelope will go on there like that, sort of. See, we'll go ahead and flare it out a little bit so it'll go over there, and we'll just slip it up on there and then seal it around the outside. What we have to do is expand this end a little bit so that our electronics will fit up inside of it. Got to do is cut it off to the correct length. We can't do anything, we have to have everything ready, because once we cut the cathode out of the other tube, it'll start deteriorating. The cathode, we got about 10 minutes that we can work with it before it ruins. So we have to have everything ready to go, so that when I cut that cathode out and weld it onto here, we're ready to close it up and seal it. Very hot, don't touch. Extremely hot, don't touch. Okay, next thing we got to do, we want to fasten these two together so that this will be held in place, so that when we do the work here, we don't screw up our positioning of the cathode. So what we're going to do is seal those together with a piece of glass rod. Okay, that fastens them together where they can't move. Okay, next thing we're going to do, we're going to need to flatten this out to make our area for the pinch. Okay, next thing to do, we're going to take the pinch and we're going to seal it onto the envelope. And then we've got to put our evacuation stem on it. Alright, beautifully sealed on there. Now the next thing we do, we pop a hole in it and fasten our evacuation stem onto it. I need to flare this tube out a little bit so that it's going to not close off on me. That puts a little bit of flare on it so we can get it fit good. Alright, for our electrodes, we're going to have our two plate electrodes. We're going to make those out a little bit heavier so that we have good RF conduction. So we're going to use this is some kind of a nickel wire here. So what we're going to have, we're going to come down, we're going to do the pinch, and we're going to put the two heavy wires like so. And our that will seal onto our plates. And then the pinch, we're going to put a piece of tungsten wire for the seal, and then another piece of heavy coming on out, and that's going to be for our connection for our RF stuff. And this will be solid glass here. All of this will be solid glass. I'm going to go ahead and clean this up. Okay, that's our piece of, and that's going to make our two pieces that connect to our plate. Alright, here's our two plates. What I did was I just took a piece of tubing, stainless steel tubing, and just cut it. And that turned out a lot more even. You know, trying to bend this stuff and get it even, no way. Now, since we're doing a tungsten to tungsten seal, or weld, we're going to have to use a little piece of nickel between it to actually melt. All right, more power. Full power. Whew, that's on there. Okay. Okay. And there it is. I'll just dress that up a little bit with the grinder, and this will be ready. Okay, now I'm going to take the grinder and just kind of dress it up a little bit so it'll sit in the seal better. Okay. See, now those are our two pieces that'll go in the thing for the, see, and then these will weld under there like that, and that's going to do it. Okay, the next thing we're going to do is put these into the seal. See, and then these are just going to weld onto there. All right. Okay, here goes. Full power, 90 amps. All right, now the other one, we've got to do the same thing. Okay, that one has to come around a little bit. Okay. Now, it has to go that way a little bit. All right. Not enough. Try this one here. All right. Well, that's going to do it. Okay, next, I need to flatten this wire out. All right. Okay. Okay, now, that looks really, really, really good. Okay, now these, okay, I'm going to bend up. Like that. All right. Here. Like that. Okay. Just to fit. Okay. Looks good, looks good. Okay. See, and then our cathode will weld across those two right there. And then these two will go out the other end. Okay, that'll go there. We'll put our seal on the other end. Okay, this one here looks like it's got a cathode in it that's going to be about the right size. Okay, I'm going to go ahead and pop it. There's the old heater. Look how that's so brittle. Woo! It's an old tube, been used a lot. Alright, now I got to get that cathode out of there. And there's the cathode. Okay, And that's going to sit in there like that. Alright, let's go get it. Alright, I'm going to have to weld the cathode first, then put the heating element and weld it. Okay. Right. Okay. The cathode's up inside there. Okay. It's still got a lot of emission stuff on it. Can you imagine trying to do this from two ends with a glass tube over it? It would be impossible. Okay, now we got to stick our heating element down the middle. Okay, and I'm going to Zorch that onto there. Alright, here goes. Okay, now I've got to adjust the position. Alright, here goes. It's right down the center. It's just beautiful. Okay, and that's insulated. The spiral of heating element is insulated so it doesn't touch the cathode. The cathode's connected on one end along with the heating wire, and the heating wire is connected on both sides. I don't know if it'll focus. I was looking carefully at this before I put it together. If you look right here, it's a hole that goes all the way through. Oh goodness. Good thing I spotted that. We got to fill that in before we put it together. That would have been a good one. Oh, it would have been a good one. Alright, now I'm going to put the getters on there. Got to have getters. Alright. Make sure. Alright, now, first thing we got to do, melt that hole shut, and then we have to seal the tube together. Okay, first thing I got to do is our seal wires have to be oxidized slightly. Okay, I'm just going to hit them a little. Okay. Now I got to put this. Okay. Big crack here. It did crack. Okay, I'm gonna have to seal that crack. We can do it. It's PYREX, so I can seal the crack. There. Okay. One of the things about using PYREX is you can go back and seal it. If this was soft glass, there'd be no way. Okay, now for this hole. I just got a little piece of tubing, and I'm just going to seal that hole off. Okay. Now, next thing we got to do, we move it up in there. All right, let me make sure all the cracks are sealed. Okay. Here goes nothing. All right. See, the heat radiating in will keep it from cooling off too fast. Here. Just fusing it together just like I was using a welding torch on steel. That's it. All right, now we got to cool it off. Then we turn it over and we do the pinch. All right, next thing we're going to do is make the pinch. We've got a crack in the base here, so we're going to have to epoxy it. It's only going to work for a matter of hours before it has air leak in. So we'll be able to see it work, but it's not going to be a long-term tube. Okay, the first thing we got to do is carefully warm it up, and then we make that pinch to seal the base. I burnt one of the wires off. Damn it, it's sticking out enough we'll be able to hook to it, but damn, I didn't want to burn that off. Okay, we'll let that cool. Alright, we got the leak detector going. Tubes on there, pumped all down. Where's my helium? Yeah. Alright, got some helium bubbles there. Alright, now, we got it stabilized. We're going to just go First, I'm going to go up in the top here. Doesn't look too good. It's an extremely small leak. Alright, let me go down here. That's just drift. That's just drift. If it doesn't go back down again, it's just plain old drift. All right. Okay, we're good on the seals. All right, let's go up here again. Okay, is everything steady? All right, here goes. It's going down. Let's just drift, and we may just have drift. This is on the most sensitive scale. There's no leak. Blacked out. It is not leaking. Alright, we're under high vacuum right now. We're down in the area of 10 to the minus 5th pour. The next thing to do, we have to heat the filament up to drive all the moisture out of the cathode. I've got the power supply connected to it, and this is a moment of truth. It either lights up and stays lit up, or it burns out. Alright, I'm just going to put a little current through it. Nothing's happening on the vacuum gauge, so we're holding vacuum good. Alright, I'm going to bring it up to... Oh, gauge went up and then went back down. It's driving water out. Now we're just going to let that sit there and vacuum. What I'm going to do is I'm going to get the oven, and we're going to oven it at about 500 degrees. I can't go too hot because I got a solder joint there. But we can go up to about maybe 400 degrees without melting the solder. Okay? So this oven, we got it set now. I'll have to let it see where it goes to, temperature-wise. There's 400. Okay, it just shut off. It's all homemade stuff. I could get a professional controller. Okay, there's at 400. I don't want to go higher than that. She came to see what's going on. You want to be in a picture? Yeah. Alright, it's sitting steady at 400. We'll leave it right there. Okay, we're going to let it cook for about 4 or 5 hours, maybe up until after lunch. Okay, the next thing, our solder connection is intact. Okay, we're going to connect up the filament in B+ and run current through it, see if it has emission. Let me get the power supply. Okay, I'm heating up the filament. This is the plate current here, plate voltage. We won't see any GM because we're just running it like a diode. Okay, I'm going to go up in voltage here. All right, there's 300 volts. Okay. We'll run the voltage up on the filament. There we go, getting some plate current. Okay, our emission is going up. We're getting 20. We have constant voltage. So what we're doing now is we're converting the barium hydroxide back into barium itself, barium oxide. Okay, we're up to 30 milliamps. See, once this is done, then we'll be outgassed altogether. That's 40 milliamps. Woo! That's some current. It's a big cathode, though. Okay, that's going to be a lot of watts. Let's see, 3, 5, that's about 15 watts. I'm going to go ahead and cut that down because what's going to happen is we're going to overheat the tube and crack it. All right, I'm going to let it cook at that current for about 30 minutes to go ahead and form that cathode good. All right. Next thing to do, we're going to flash the getters. There's 2 getters in it. First thing I'm going to do is warm each one of them up to red hot, but not flash it. And that'll drive the gas out of them. The pump will pump the gas out, and then we'll flash them, and then we'll seal off the tube. Now just make them a little red hot, and that drives the gas out of it. Do the other one. Give it a few seconds. Doesn't take it long to pump the gas out. Okay, here goes. We'll pump the back one first, or flash the back one first. Whew, not getting any flash. They're bad getters. A little out of that one. Now we'll seal her off. There it is. All right, let that cool so I don't burn my fingers. Well, total disaster. One of the seals apparently leaked. So we got gas in it. It isn't going to work. Okay, you can see when I bring a little voltage onto it, we got the blue glow up inside of the gas. Woo! A million amps. Woo! It just instantly runs up to high current. There's so much leaking in, the getter doesn't have even a chance of absorbing it all. It's already saturated the getter. All right, so this one's good for display, but as far as operating it, no chance. Okay, well, I'll have to think carefully. Do I do another one and make a try for a working one, or just say, hey, you know, it was a good try, fun project, but, whew. But what happened was, when I made this pinch, I did it wrong. I used the main tubing as the pinch. What I should have done is taken a smaller piece of tubing and flared it and made the pinch in the small tubing, and it would have been a much cleaner pinch. This one here did okay. You know, that one, that's the way I did this one here. I used that smaller piece of tubing, piece of 1/2-inch tubing, did the pinch in it, and then flared it out and sealed it to the larger tubing. And I should have done that with this other one. I figured I could probably take a shortcut and do it anyway, but nope, caught up to me. It was just too much of a mess. You know, all that business of sealing holes and cracks and stuff, it just, it wasn't going to work. So this one here will go in a tube collection just as a display of, hey, this is what a primitive magnetron looks like when someone tries to make one. Yeah, hey, there's people who collect stuff like this. Okay, that's it.